Hello everyone, welcome back to my channel. In this video, I'm going to talk about basis for a topology. This is a very important topic in topological spaces. Let's get started. Let me begin with the definition of a basis for a topology. Let X be a topological space and let B be a collection of open sets. That means B is a subcollection of tau, where tau is the topology on X. If for every open set G, there is a subcollection B prime of B such that G can be represented as the union of all elements of B prime, then B is called a basis for the topology tau. What does it mean by this? First of all, B must be a subcollection of tau. The second condition says that any element of tau, meaning that any open set, can be represented as a union of elements in this collection B. So, there must be a subcollection B prime of B such that we have this representation. To better understand this concept, we are going through a very simple example. In this example, X is the set consisting of three elements A, B, and C. And tau is the discrete topology on X. Here, I list all elements of tau, which are all subsets of X. Now, we consider the following collection of open sets. B is the collection consisting of three single point sets in this topological space. Let us show that B is a basis for the topology tau. First of all, every element of B is an open set. Secondly, we need to show that any open set can be represented as a union of elements of B. Let's take this open set A. This is a single point set. It is a union of a collection of sets in B, namely the collection consisting of only this single point set A. And it works similarly for this set and this set. How about this open set? This open set can be represented as the union of two elements of B, namely this single point set and this single point set. Similarly, this set can be represented as the union of two sets in this collection over here. And it works similarly for this set. Finally, X is the set consisting of three elements A, B, and C, and it is the union of three sets in this collection. Okay, therefore, by definition, B is a basis for the topology tau. Let me continue with a very important theorem. This theorem allows us to check whether a collection B of subsets of X is a basis for the topology tau or not. Okay, let X be a topological space and let B be a collection of subsets of X. Then B is a basis for the topology tau if and only if the following conditions are satisfied. The first condition is B is a subcollection of tau. Again, it means that every element of B is an open set. The second condition says that for any open set V in X and any X in V, there must be some basis element B such that X belongs to B and B is a subset of V. Okay. Now, the second property here can be illustrated in this figure. It says that no matter what open set V we take, and for any X in V, there must be some set in this collection B such that X belongs to B and B is a subset of V. Okay, let's go through the proof of this theorem. First of all, we assume that B is a basis for the topology tau on X. By definition, B is a subcollection of tau. We also know that, again, by definition, any open set can be represented as a union of elements of B. Okay, so we are going to take any open set V and any X in V. We need to show that there is some B in this collection such that X belongs to B and B is a subset of V. Because V is an open set, and B is a basis for the topology tau, we can write V as a union of elements of this collection. So V can be written as the union of all sets in a subcollection of B. Now, because X is in V, it is in this union, so it belongs to a set in this union. So there must be some B in the collection B such that X belongs to B. How come that is true? B must be in this collection B prime, and because B prime is a subcollection of B, X belongs to the collection. I'm sorry, B belongs to this collection. Okay. This completes the proof of the necessary condition. To prove the sufficient condition, we are going to take any open set V. And because the second property here is satisfied, if we take any x in V, there is an open set B sub x in B such that x belongs to B sub x and B sub x is a subset of V. Um, this follows from the second condition here. However, we use B sub x instead of B to indicate that B depends on x. And thus we have the representation V is the union of all B sub x where x runs in V. How come this is true? Because B sub x is a subset of V for every x in X. If we take the union of all of them, the union is still a subset of V. So we have this reversed inclusion. To show that this inclusion is satisfied, we are going to take any x in V. Then x belongs to B sub x, and B sub x is a subset of V. So x belongs to B sub x, so it belongs to this union, which shows that V is a subset of this set. Now, by this representation, we see that V is a union of elements in B, and therefore B is a basis for the topology tau. Wow. Next, we are going through an example in order to better understand the theorem. Let's look at the set X, which is the real line in this situation, and tau is this collection. An element of tau is either the empty set or any subset of R that contains 0. Then we can easily show that tau is a topology on X. Now we consider the following collection B. B consists of all sets of the form 0x where x runs in X. So if X is non-zero, every element in this collection consists of two elements, namely 0 and X. And if X is 0, then the single point set 0 belongs to this collection. Let's show that B is a basis for the topology tau. It is obvious that B is a subcollection of tau because every set in this collection contains 0, so it belongs to tau. To show that B is a basis for the topology tau, we are going to show that the second condition in this theorem is satisfied. So we are going to take any open set V and take any element of V. Since V belongs to tau, and here V is non-empty because it contains X. So V contains 0 as well by the definition of tau. Let B be the set consisting of 0 and X, then B belongs to this collection. Okay. And it is obvious that X belongs to B and B is a subset of V. Okay, therefore B is a basis for the topology tau. Finally, we are going through a very important example involving the metric topology. So let X be a metric space. Recall that the metric topology is defined as follows. A set V belongs to tau if and only if for any x in V there is some radius r such that the open ball with center x and radius r is a subset of V. Now, we consider the collection B of all open balls in this metric space. Okay. Then B is a basis for the metric topology on X. How come this is true? We are going to use a very important fact that any open ball in this metric space is an open set. So B is a subcollection of tau, meaning that every element of B is an open set. And if we take any open set V and any X in V, there must be some radius R such that this open ball is a subset of V. And remember that this open ball is an element of this collection and X belongs to this open ball, which is obvious. So by this theorem, B is a basis for the metric topology on X. Finally, we can show that the collection of all open intervals is a basis for the usual topology on R as a particular case of this. This completes my video on basis for a topology. Thank you for watching.